Swayam Prabha. Digital India. Educated India.
So, hello everyone. Hope you all are doing well. My name is Mukh Bansal and I'm a postdoc at Interdigital Research and Innovation Lab in a city of France called Rennes. And I worked in the area of geometry processing and computer vision. And at the moment, I'm involved with a project named Digital Double, where the idea is to mimic a real world character virtually. And there are several aspects of it. For example, how to represent a virtual object, how to represent its movement or deformation, and how to interact with its surrounding. So in this session, I'm going to focus on how to formalize the motion or deformation of a virtual object, and which is known as shape deformation. Before we start, I just want to mention a couple of things regarding this session. So this session is more inclined towards a hands-on session, and I don't intend to bombard you with a lot of content. Rather, my aim is that by the end of this session, you should be able to implement basic shape deformation algorithms. And to make it interesting, we are going to have two lab sessions, one in the morning and one in the afternoon. We are going to use Python and libigel for the lab. If you have used libigel before, then it's good. If not, then no worries, because we are only going to use libigel for displaying the results for not much computation. For everything else, we are going to use Python and NumPy. Also, all of us know how boring an online session can be, so you can try to make it interesting by asking questions. And you can use the chat window in the to post any question you might have. Okay, so let's just start with shape deformation. And what is shape deformation? So in the figure, you can see two digital representation of an octopus. In these representations, the tentacle shown in red is at different positions. So we call both representations as deformed version of each other. Uh, it is possible to deform any given object in numerous ways, and it is this process of deformation that we want to model mathematically. Now, to gain more insight, let me give you an example from the demo domain of animation. So let's assume that we have a 3D object, a humanoid in this case, and we want to generate an animation of this object performing some action. Let us say that these are the sequence of poses needed to generate the animation. So in red, you have the reference object, the given model, and in greens, we have the deformed model at different point of time. Now, typically, a digital artist design these poses given the reference model. But this is an involved process and it demands a huge amount of time even to generate a single pose. So to reduce the required time, a set of these poses are selected as keyframes. So these, let's say these are the keyframes. And now only these keyframes are designed by the digital artist. Once the keyframes has been selected, the intermediate poses between these selected keyframes are generated by an interpolation process, which is usually faster. Now, in order to generate keyframes, the digital artists are supported by interactive tools to deform the reference model. This process is called interactive shape deformation. Typically, certain portion of the reference model called handles are selected and moved around to get the desired pose. So for this example, this is the reference pose. These are the keyframes which we have selected, and the green markers on the reference pose represent the control handles which are being moved to different points in order to get the desired mm, pose. Uh, for this task, a variety of methods exist which can be divided into two classes, namely direct methods and variational methods. For variational methods, based on the final position of the handles, an energy is minimized uh, based on the geometry of the reference model, which gives us the desired deformed model. While in direct methods, a rig is used to achieve the deformation of the reference model. And we are going to discuss it in more detail. Once we have the keyframes, an interpolation algorithm is used to generate the intermediate poses. So the idea is to generate these intermediate poses given these two keyframes, and while preserving certain geometric properties. So we would want to preserve the shape of the reference model uh, such that the intermediate poses also looks like from the same class. Now, these interpolation algorithms are also inspired by shape deformation algorithms. Repeating this process will provide us the desired animation. So this interpolation is for the first pair of keyframes. Then this interpolation is for the second pair of keyframes. And then if you combine both, you get your desired animation, the final sequence of the animation. So today we are going to see different frameworks to generate these keyframes and hopefully implement them. So let us start with a direct method popularly known as skinning. There are three components of any skinning framework. First one is a control structure. A control structure provides an interface for specifying the movement for the different part of the reference model. And the control structure defines what kind of motion or deformation the reference model can exhibit. So a control structure can consist of different type of control handles. The first one is the point handles. So point handles are the points on the reference models which can be moved freely in space. And this setup is similar to the setup of a puppet. If you have seen a puppetry show before, where you choose some points on the puppet and you attach string to those points, and then you move these strings, and then the puppet moves as the string moves. So typically, these point handles are useful for object with no rigid structure. For example, the octopus. But quite often, there are parts of the reference model which exhibit rigidness. So in other words, these parts can only rotate or translate, while stretching and bending of these parts are not allowed. So for example, limbs of humanoid model will fall into this class of objects. So for these parts, a bone handle is used. So bone represent that it is not going to, it can only rotate and translate, but it you cannot stretch or bend a bone. Now, in case the reference model can only exhibit local rigid motion, a more elaborate structure called a skeleton is used. The skeleton is a combination of connected bones such that the motion of the bone has some impact on the connected bones. So for example, if you move this bone over here, we might want to apply the same motion on the on this bone over here. The point where two bones are connected is known as a joint, and most of the time the motion is specified with respect to these joints. Skeletons are very popular control structures in motion design and tracking applications related to humanoids and quadrupeds. Uh, and automatic skeleton computation is a huge topic in itself. Interested people can read a very nice survey by Tagliasachi over here. Finally, another interesting choice of control structure is cage handles. The idea is to constrain the space around the reference model using cages. The deformation or the motion is applied on the cage vertices, which in turn is transferred to the space inside the cage. And it is completely possible to mix different kind of control structures, and most of the time such is the case. Also, the control structure is defined based on geometrical structure of the given reference model. So in that sense, it's a personalized setup. So if you have a different reference model, you might need a different control structure. To keep things simple, we are going to use point and bone handles most of the time in this session. Now, second component of the skinning is the weights. Weights represent the influence of the control structure on different parts of the reference model. Now, for example, now for each handle in the control structure, you need to define a region of influence. For example, one would not want point handle P to have any impact on any other part of the reference model other than the palm. Or in other words, if we move point handle P, then the only region near to the point P1 should move. Similarly, for point P2, the region of influence should be in the vicinity of point P2. The strength and the region of influence of a control handle is specified by a weight function, which is defined over the reference model. So for each control handle, one weight function is defined. So assuming the reference model is represented by a mesh, and I hope you all have seen a mesh till now. The weight function is defined for all the mesh vertices. In the figure, the strength of the influence is captured by the brightness of the color. So for example, the weight function for point P is highest at point P, and it gradually decreases as we move away from the point, so in this direction. Similarly, the weight function for point 2 is maximum at point 2, and then it decreases as we move away from the point. So it decreases in this direction as well as in this direction. Then we have weights for bones. So where, for example, bone B1, this region has more or less same weight value, but the weight decreases as we move away from the bone. So we can define weight functions for any control handle, and it's a topic of research again. So a lot of research goes into how to define weights, and we are going to see some type of weight functions later in this session. So a control structure combined with these weights is also called a rig. Now, once the control structure is defined, one can specify the desired motion or deformation using transformation on the control structure. For each handle of the control structure, be it a point handle, a bone, or a cage, a transformation is defined. Typically, a rigid transformation, for example, a rotation, and a translation is used. But depending on the requirement, scaling and shear transformations can also be used. Uh, Let us assume that we have a skeleton as the control structure. Then a skeleton in green shows the initial configuration of the control structure, while the skeleton in green shows the final configuration. So T1 is the transformation for bone B1. So this is the transformation which you want to apply on bone B1. And in this case, in this particular example, it's a rotation transformation. Similarly, Tj is a transformation for bone Bj. And you have to define transformation for each bone or each control handle in the control structure. Also, so you can see that there is only one bone which goes under some change. So if there is no change in the control structure on the handle, an identity transformation is used. So in this case, transformation corresponding to bones other than B1 are all identity transformations. And as B1 is the only transformation which is B1 is the only bone which is moving, so we are only going to need the weight function corresponding to B1. And then if you apply it on the reference model, you can see a intuitive motion happening. So this was the initial configuration of the hand, and then this is the final uh, configuration of the hand. So you can see that the motion corresponds to the motion of the control structure in some sense. And this case is easy because there is only one active bone. There could be scenarios where a part of the reference model is influenced by multiple control structure, multiple control handles. There, the transformation acting on a particular part is blended before applying on the part. And by blending, I mean the blending simply can be seen as a weighted average of transformations. And there are multiple ways of blending transformation. And again, we are going to see some of them. So now we need to formalize things a bit before we move ahead. In case you have any question, you can ask, and otherwise we will move ahead. Assuming that there are no questions, let's start formalizing things. So the reference model is represented by a mesh with n vertices. Vi's are going to represent the vertices where I varies from 1 to n. And there is no constraint on the topology of the mesh. So it can be a triangular mesh, a quad mesh, a hybrid one, or maybe a volumetric mesh, whatever mesh you have. Now let's assume that the control structure consists of M control handles, and we are going to represent control handles by H subscript J, where J varies from 1 to M. Again, these control handles can be point handles, bones, or cages. For each control handle, as we have discussed, we have a weight function defined on each vertex of the mesh. So Wij represents the weight of jth handle for ith vertex of the mesh.
Subuk, Sorry
Yes,
to
sir.
interrupt. I think there is a question by Vignesh in the chat. Unless you already addressed it, I'm not sure. Vignesh, maybe you can speak out.
Yeah.
Vignesh, are you
Uh,
there?
Yes, sir. Hello. Am I
yes.
audible?
Yes.
Okay. No. I missed that technical term you said for control handles and weights. I was making notes, so I'm sorry.
So it's called rig.
Rig.
RIG rig.
Okay.
Yeah.
So thanks.
Okay. So yeah. So weight functions. Weight functions are defined for each handle and for each vertex of the mesh. So Wij represent the weight of jth handle for ith vertex of the mesh. For each control handle, one transformation is defined, and these transformations are represented by Tj. Again, J varies from 1 to M. Now, using skinning, for each point on the mesh, let's say we choose point Vi, the transformed or deformed vertex V dash Vi dash is given by this expression. Now let's decode it. So Wij over here is the weight of handle H1 at vertex Vi. T1 is the transformation corresponding to handle H1. So essentially, what we are doing over here is that we take transformations for each handle, apply it on the vertex Vi, and then take a weighted average of it. Or we can think about it the other way around. So we take weighted average of all the transformations, and then we apply it on the vertex Vi. This weighted average of transformation is also known as blending of transformations. So in the simplest case, one can just take a linear average, linear weighted average, just like in this case. And the resulting skinning framework is known as linear blend skinning. So we are going to implement it, but before that, let's take a look more closely on certain concepts which we have seen till now. So as we have seen till now, that the importance of weights is very, weights are very important in the skinning framework. Let's take a look at some simple ways to define these weights. So defining weights is not a trivial process. Traditionally, a digital artist design or paint weights to get the desired deformation. And this process is based on trial and error. So the digital artist would paint the weight, then perform skinning, and then check out the result and see if there are any problematic regions. And if there are, then the weight would be updated accordingly. And then he will again repeat the skinning process and see the results, check the results. So automatic methods to compute weights reduce this time and effort needed in this process. The simplest set of weight are computed based on the distance between the control handles and the vertices of the reference model. A rigid weight, for example, are the weights which are set to 1 for handles which is closest to the vertex. For any other handle, the influence is set to 0. The weight is set to 0. So that way, only one handle is going to influence any vertex. As you can imagine that these weights are not going to be continuous, and we start to get artifacts at vertices which are equidistant from two or more handles. Another type of weights are called inverse distance weights. For each handle, uh, the weights at a vertex vi is defined as the inverse of the distance between the handle and the vertex. And p varies from 1 to infinity, whatever you want to take. It will give you different variations. Now, in this case, uh, the weight, these weights are going to have a global impact. For example, P1 will have some impact on the vertices, maybe on the foot of the model, because you will certainly get some distance between P1 and the vertex over here, and which is not desirable. Furthermore, the Euclidean distance between the handle and the vertex Vj, uh, it does not work well if we want to define a notion of closeness. We can imagine that even though the distance between point P1 and a point over here uh, is small in the Euclidean sense, but it's a large distance if we want to compute the distance on the shape. So in some sense, the weights are not shape aware, and to take the geometry of the reference model into consideration, the geodesic distances are used.
Sir, hello.
Yes.
Sir, control center, all the points on skeleton, right?
So control handles is a generic term. Like so, skeleton is one of them. So it's a set of different sort of elements. Like you can define point as your control handles. You can define bones as your control handles.
So that
And
should
you,
be
if you,
so that should be associated with skeletons. Uh,
not
is it right?
necessarily. So no, so it's completely possible to define control handles without using any skeleton. So like in this case, you can see that there are only points, and it's a completely valid set of control structure. So control hand, so there might be confusion with the two terms. Control structure is the overall structure, overall caricature in some sense, which is going to govern the motion. Control handles, on the other hand, are the elements. So like, let me just see if I can. So it's like points. So you can use point handles to define control structures. Then, so let me just go back. You can use point handles to define the control structures. Then you can combine these points with bones. So in this case, you have point control handles as well as bone control handles. So this is a case where you are using both of them. Then you can define skeleton, and you can also mix skeleton with point handles and other bone which are not connected to each other. A skeleton in some sense is one one unit where every bone is connected to every other, so every bone is connected to some other bone, and it's going to move in coherence in some sense. And on the top of it, you can also define cage control structures. So in some sense, all of these are control handles. Does this answer
Okay,
your
sir.
query?
Yes, sir. Makes sense. Thank you.
Okay. Okay. So overall, the skinning weights which we need needs to have certain properties. First, they should be continuous and smooth, and gradually decrease from the control handles. Then, as we have discussed, they should be shape aware. And they should also be local and sparse. And by sparse, we mean that only a small number of control handles should impact any given vertex. And at last, the weights should be non-negative and bounded. So negative weights are unintuitive in nature because it's difficult to understand the implication of a negative weight. When you add or subtract negative weight in the scaling equation, it doesn't make sense, and it's difficult to predict how the model is going to behave. Then boundedness is important to preserve the shape of the reference model in absence of any deformation or transformation. And boundedness is implied by a partition of unity, which says that the sum of the weights at any vertex should be equal to 0. It's not very difficult to understand. So this is your scaling equation. This is your scaling equation. So let's say that we apply same transformation on each control handle, which is Ti in this case. So we can take Ti out of this expression. And now what we are left with is sum of weights multiplied to the transformation Ti applied to vertex Vi. So we can write it in this expression over here. And now if you take Ti as identity, that means there is no transformation being applied on the control structure. So if you put Ti equal to identity, you are left with this expression. And even though you don't have any transformation applied to vertex Vi, you are still going to get a scaling effect, which is equal to this scaling term being equal to the summation of these weights, and which we don't want. We would ideally want that if there is no transformation applied to the control structures, we would want to preserve the shape, right? So that's why we need to normalize the weights, and this partition of unity properties become important. Now, based on these properties, uh, weights can be computed using an energy minimization framework, where an energy is defined in addition to some constraint. One can use a different type of energy functions. One popular one is called Laplacian function, Laplacian energy, and you might have seen it in one of the earlier session in the summer course. Intuitively, minimizing this Laplacian energy is going to provide you smooth weight functions, and other desired properties are added to the minimization function in form of constraint. So we can add non-negativity and bounded constraint. We can add a partition of unity constraint, or sparseness constraint for that matter. For our labs today, you have been provided with weights computed using this reference, which we call bounded biharmonic weights, BBW for short. And these are nice weights which include all of these properties. I'm not going to discuss it in more detail because it's a topic in itself. But if you are interested, I mean, LD by GL function is also available to compute this weight if you want to try it out. Now let's talk about the representation and blending of transformations. Again, blending simply means mixing or taking a weighted average of the transformation. So in skinning, typically a rigid transformation is used. A rigid transformation consists of two parts. One is rotation transformation, and one is another part is the translation transformation. So given a point V, we can rotate that point by applying a rotation transformation R followed by a translation, and we get our transformed point V dash. Alternatively, a rotation and translation can be arranged in a 4 cross 4 matrix E, which can be applied to a vertex to homogeneous representation of the vertex V tilde. Now, the translation can be represented using a vector in R3. And if applied alone, it's a very simple transformation to work with. One can linearly blend multiple translations. But the case with rotation, on the other hand, is not that simple. And there are several ways to represent and blend rotation transformations. The simplest one being the Euler angles. Euler angle representation consists of 3 rotations, theta x, theta y, theta z, around 3 mutually orthogonal axes. Typically, the choice of these coordinate axes are x, y, and z, but you can take any mutually orthogonal axis. In literature, these rotations are also called roll, pitch, and yaw due to their use in traditional navigation systems. Euler angles are a popular way to represent rotation in navigation systems. It's easy to represent these rotation in matrix form by Rx, Ry, Rz, and any general rotation can be represented as a composition of these matrices. But despite being compact and easy to represent, easy to use representation, Euler angle representation is ambiguous in nature. By that I mean that for any general rotation, multiple Euler angle representation exist, and hence usually Euler angles are avoided. There is one interesting issue called gimbal lock, which is very famous if you are working with Euler angle representations. In that case, in a certain configuration, you lock a degree of freedom. I'm not going to go into the details, but it's interesting. It would be interesting for some of you to just go to just check it out on the internet. Another representation for rotation is called axis angle representation. And as the name suggests, any rotation is represented by the axis of the rotation and the angle of rotation theta. So axis of rotation is represented by n, and the angle is represented by theta. And using Roderick's rotation formula, axis angle representation can be converted into a matrix form. It's very easy to derive this formula, and we are going to see a part of it later in this session. Note that this matrix NX is a skew-symmetric matrix defined as follows. So for the moment, we are just going to assume that we know how to define a rotation using Roderick's formula and move ahead with it. And this is what we are going to start our lab with, actually. And we are going to see the implication of it in the lab itself. So we now have all the concept needed to implement our first interactive shape deformation algorithm, which is going to be linear blend skinning. And we are going to take a simple example for this case. So the example we are going to work with is a simple object, which is a rectangular bar. The control for control handles, we are going to take 2 points. One is 2 points each one on each extreme of the bar along the length. Then for these these control handles, we need weight functions. One set of weight function has been provided to you, and another set of weight function you are supposed to compute. Then for each control handle, we need to define transformations. For the lab assignment, we are going to just focus on rotation transformation, and then we need to perform linear blend skinning. So I will now show you how to run this, and after that we are going to start our first lab session. In case you have any question, you can ask now.
Sir, I have checked out that the problem to solve the problem of gimbal lock, there is a term called quaternions. So
Yeah, we will see it. We are going to discuss quaternions
okay.
later in this course.
So what is SO3?
Okay, so SO3 is the group of all rotation transformations represented as a 3 by 3 matrix. So I don't know if you are familiar with the groups. Are you familiar with groups?
I have been introduced to it.
Okay, so it's like when you take all possible rotations, there are certain properties this set of transformation can follow. And so rotation transformations, if you take a set of it, they follow certain properties, and that's why it's called um, the term is spatial orthogonal group, right?
Oh,
So
thank you.
we are yeah, we are not going to go into detail, I mean, about the mathematics of the group. I just mentioned because some of you might be from the mathematics background, and for them it might be interesting to see that there is a group into picture. But today, I mean, I'm not going to use too complicated math words. I just want to focus on the implementation part, and which is what we are going to. So there are a couple of tasks which you need to perform. So I will just go through the entire file and let you know where you have to do your task. So the first box over here is just the import of usual IGL and some function from matplotlib, which we need to plot or display our results. Nothing major. Then in the second cell, it's more or less reading of the mesh file. So V and F are going to represent your vertex array and your face list. Then these are the handle indices, one at the top and one at the bottom. And it doesn't matter which one is which in this case, because it's very simple. So these are the indices of your vertex array V. So your handle points are V25 and V74. So you can plot your mesh using the plot function, which is given by IGL. So if you look at it, this is your rectangular mesh. Okay. Then you have weights. One particular type of weight function has been provided to you, and which is the default setting. So if you load these weights, this is what you're going to get. And again, these are color coded, so you can see that you can easily guess which one belongs to which handle. So this is going to vary from, so this is the highest point, this is the lowest point, so the handle should be somewhere here, and same for the second weight. So the first task for you would be just to implement the inverse distance weights over here, and then see how different they look, I mean, by plotting them. Then you need to implement Roderick's formula to get the rotation. You are going to specify a axis of rotation and a angle for rotation, and then this function should output a valid rotation. And I mean, it's not very difficult. It's just a couple of line of codes. So just don't feel that it's going to be too hard. And most of the time I provided relevant information which you might need in order to implement things like this formula has been provided to you here, and you can also check out the Wikipedia page if you want to have if you want to go through more information. Then this is the function blendMat, which is a function for linear blending of matrices, and this is you're going to implement for your linear blend scaling. If you have completed these tasks, then you are going to use these two functions in the skinning function. So in the skinning function, you are going to take as input the set of vertices and the weights and the transformation. And for transformation, we are going to represent a transformation in the axis angle format first, and then we are going to convert these axis angle representation in the skinning function. So in the skinning function, you don't have to do anything. It will work just fine. You just have to implement the Rodix formula function, blendMat function, and the weight function. And once you have this, you can just run it. And once this part is okay, you should be able to see your results. And for the results, you need to define the input parameters. So NH over here represents the number of handles, which we have already defined in the over here. Now, for handle transformations, there are two handle transformation, and it's easy to make sense of it. It's axis angle representation. So the first parameter is your angle, and then rest three parameters are the axis of your rotation. And so if you perform this, you should be able to see the result. At the moment, you won't be able to see anything because the task is not complete. And I just want you to play around with different configurations of these input parameters and see if they make sense to you. As a last task, you should just reproduce what we call the candy wrapper effect. And after this lab, when we are going to start our next session, we are going to start discussing about this candy wrapper effect. So this is going to be our starting point for the next session. Okay, so now you can start implementing it. I'm available. If you have any doubt, you just ask. Now, in the inverse distance ways, I guess it's a couple of line of code which you need to implement. The important thing was that you need to compute the distance between the vertex and the handle. And then so I will just show you different kinds of weights. So maybe one would be just to say, so one you have to implement. Let me show you the rigid weights. You can see that it's intuitive. And if you remember rigid weights, it was assigned. So for every vertex, the weight is assigned one only for the handle, which is closer. So in this case, these vertices closer to handle at the top, and these vertices are closer to handle at the bottom. So you get the respective weight functions. Then for Roderick's formula, you need to define the skew symmetric matrix, and then it's just a simple formula. So if you run this, and then for blending, you just need to blend transformation at each vertex according to their weights. So again, 2 lines of code here. Run this, and then if you skinning part, so this is the main part where you are calling the skinning function with different parameters. So this is going to be with, by the way, this is with rigid weights. So as you can see that this is the result you are going to get, and you can see that the object behaves rigidly. So it treats the complete object like it has 2 components, but you can see that the discontinuities are creating artifacts. We don't want this to happen. You can use different transformation. Feel free to explore it. Let me just show you the results with the biharmonic weights. So these are the weights, and then if you run the same example, this is what you are going to get. But this is one particular case. You can, if you run the next cell, you will see that this is what you are going to get, and we are going to discuss this why why we are getting this, and what can we do to rectify this. But for the moment, I just want you guys to just implement this and see, I mean, if you can make some sense out of it. Okay, I will share the code as once the session is over. You can play with the code if you have not implemented it yourself, because in the next session we are going to build on this code, and if you haven't done it, so it won't be as interesting as it should be. So